handwritten digit as a 0 or 1, or categorize incoming mail as a spam or a normal one. Then in the multi-class, you have extend those classifier for all the possible 26 classes. In the English alphabet, you get a 26 class classification problem. Or if you extend to all the digits in that handwritten digit recognition, then it becomes a 10 class problem. And in multi-class, you can have some RGB images where you have more than one object of interest, and you need to map them into more than one label for every data item or every image. And these are the possible most important classifiers. And we have seen k nearest neighbor, which does by taking only the distances. The nearest neighbor here is basically the distance metric, and the distance metric can be either Euclidean distance or Mahalanobis distance or Manhattan distance, anything you can choose. And in the decision trees, you have two main algorithms, ID3 called iterative dichotomizer, and the classification and regression tree, where your data, from the data, you can generate a decision tree having an uprooted tree where you have a root at the top and terminal nodes at the bottom. Each distinct path from the root to the terminal node becomes a rule, and the disjunction of each rule is the basic discriminant. We do it in the decision tree. Then comes the multi-layer perceptron. So basically, this is a type of artificial neural network, where perceptron is a type of network and multi-layer perceptron is a special category of artificial neural network, which basically does the simulation of a human brain. So a particular neuron in a human brain will does lots of computations. So we'll simulate it like this. We divide the neuron into two parts, where each neuron will take some inputs like this from an external source. Let us label it as x1, x2, and xn. And for each connection, we have assigned a weight, just like the data passage in the human brain from one nerve to the another nerve through some electrical impulses. That impulse will be the passage of the data is depending on the strength of that connection, a thick connection or a thin connection. So that the thickness or the thinness of the connectivity of one neuron to the other is simulated through the weights. And here a summation unit, we do the sum of the products of the inputs and the corresponding weights, and an activation function, we use it to determine an output y. So this simple, so we add one extra input called bias input, which has a label x0 with a value 1, and the corresponding weight is w0. So we call the z as the summation of xi wi, summation ranges over I from 0 to n. So this is again looks like a typical linear regression, and then we apply this z to get the output y. So this is once again for a logistic regression like thing. So using this, so this is for one neuron. So this is the simplest neuron called Macula-Pitts neuron model, the inception model. So like this, you have a set of neurons. You can have, these are the input neurons. And let us say we design a feed-forward neural network for a binary class problem. So this we call a feed-forward neural network. Or also called multi-layer perceptron. And we add another layer in between And we'll have, so these are the inputs. Say this is the bias input and the other inputs. And from every neuron here, you will have connections to each and every neuron in the next layer or adjacent layer. So these weights, we call it as a W0, 1, means this is the first neuron in this layer. W02 means IWIJ, where I representing the neuron in the previous layer and J representing the neuron number in the next layer. So like this, you have the connections. So this is a W. Let us say there are M neurons here, 0M. So this becomes W11 and W12 and so on, W1M. So this is the, and here from this once again you have the neurons like this. Since it is a binary class, you can have a single neuron. This value will be either 0 or 1 for a binary classification problem. So this we call it as an input layer, and this we call it as a hidden layer, and this output layer. Because input, we supply input to the neural network, and output, we receive the output from the neural network. And hidden because neither we give the input directly to these neurons in this layer, nor we receive the output directly from this layer. So the input is from the previous layer and the output is to the next layer. So we call it as this is a hidden layer. So in this way, you can design for a multi-class, let us say for our digit recognition, we have a 10 class problem. So typically how we can see is, let us say I have an image, let us say that it is an image of 8 cross 8 and having the digits return, let us say like this 3 or 1 or 2, whatever, one digit per image. And let us assume that whatever is written is black and the background is white. So there are totally 64 pixels, out of which some pixels are off, representing the corresponding character. Or in the other way, let me put it in this way, change the background. Uh, okay, 1 second. So like this, if you can, I hope you can see the screen right. Can you see the screen?
No, sir, not yet.
Okay, I think share again. Now,
Yes, sir.
so I just what I did is to change the background to black color, and
Okay.
so a typical image. So if you see that image like this, an 8 cross 8 cell, so where you have the uh, 8 rows and 8 columns. Okay, let us assume that this is 6 and this is also 6. Okay, so here's 1, 2, 3, 4, 5. Okay, I have only 5 rows and 6 columns. So I represent the number 3. So by just a pixel, each cell is a pixel here. So I have the pixels on. So this represents, you can see that the architecture is like 3. I hope you will visualize the 3 here. So you have this, if you take this, totally 30 pixels are there. So we divide, we make a neuron with 30 inputs and one bias, 31 inputs. Let us say this is the X naught having the 1, and these pixels are X1 to X30. So since there are 30 pixels total, so if you make it as a vector, so the black will be represented 0 and white as 1. So this is like a 0 and 3 whites, so 1, 1, 1 and 2 blacks, and then 3 blacks and a white and 2 blacks like this. You have the last row 0, 1, 1, 1 and blacks. So this is how the 30-dimensional vector look like. So and you have, let us say, around 6 input or 4 inputs in the hidden layer. And since this is a 10 class problem, you have the number of classes either 0, 1, 2, 3, 4, 5, 6, 7, or 8 or 9. So let us say in a generous case you have 10 neurons in the output layer, and some neurons in the hidden layer like this, and your inputs will be like, I'm not drawing all the connections, so you will have this, let us say like this, the neurons. So each neuron will be exhibiting some output like this. So depending on that, since we have 10 neurons, if all the neurons say 0, so we have 10 neurons. So if all the 0, we get 0, let us assume that this is a class 1, and you have one neuron here representing class 1, and you have like this representing class 2. Like this, you can divide it for all the 10 classes. And this is a typical multi-layer perceptron with the topology, means the number of neurons in every layer, 30 neurons in the hidden input layer, and let us say you have around 20 neurons in the hidden layer and 10 neurons in the output layer. This is a typical topology, and the weights you have are 30 into 20 plus 20 into 10. So many weights. So here you have 600 plus here you have a 200. Totally 800 weights are there. And you are going to use this sort of a network to classify the given the character given present in the given image, whether that is either 1 or 2 or 0 or 9. So this way, this is what a multi-layer
कहाँ जाओगे?
requires
कितने
the to mute your phone.
नहीं देख.
So when you do this like this, once you start with some, let us say you have around 100 images, you have each category 10 images, let us assume. Out of these 100, I use 70 images for training and 30 images for testing. Means 0 images I'll take 7, 1 images I'll take 7. Like this, per category I'll take equal distribution of 7 images. Totally for all the 10 classes, 70 images I'll get, and then I use them for training purpose. So when these weights are initially random weights, initialized with random values that lies between 0 to 1. and the corresponding outputs also we assign it for every pixel, for every image. Then what we do is when you start with this in a random weights, you may not get the predicted output. So what we do is we try to find the error in for every input. So in a simple way, I have this input layer represented like this, and I have a hidden layer represented like this, and I have an output layer represented like this. So I give the first input and we have the connections here, and based on the connections, the processing, every neuron you have the same sum of the products, and apply that output to the activation function that transforms that output into some 0 to 1 value, and you pass those outputs from the hidden layer to the output layer and you get the output. So this is the output you get OP, and your desired output is something different. Desired output is D. Then you calculate the error as the difference between, absolute difference between these two outputs as the E. Or sometimes in order to avoid this absolute difference and all, we take the least square error. And then what we do is we try to, based on this error, we try to take the partial derivatives and adjust the corresponding weights between hidden to the output and between input to the hidden layer. So that adjustment of the weights, we use back propagation algorithm. To do this learning. So after the weights get adjusted, we have 70 inputs. So the first input we have given first time, and we get some error, and we adjusted the weights. So we go back, and with the adjusted weights, we take the second input and make a forward pass. And for that adjusted weights for the previous input, we are giving the second image as an input. So naturally, you will get again some error. So like this, you make a cycle of all the 70 inputs you run, means 70 times these 300 weights, 800 weights get adjusted. But once you are given the 70th input, you are not sure that those weights will be able to recognize all the 10 classes properly. So once you make 1 to 70 over, means one cycle of inputs is over, means you can say that one epoch has been finished. Then you start with the second epoch. So if you do this, this is what the learning happens. If you make a plot between the number of epochs, which is on the x-axis, and the mean square error for every epoch on the y-axis. So the first input I get a E square. So let us say that is E1 square. And for the second input, I get a E2 square. And then for the 70th input, I get E70 square. So I take the average of this summation of all these things, EI square, and multiplied with the 1 by 70, I get the mean square error. So if you make the again second epoch, third epoch like this, you do it, your error will be reducing, and finally at some point it will make a constant line saying that at this position where you have no further change in the mean square error, you can stop the learning. So some people will use the change in the mean square error should be very minimal, or some people use 1000 epochs or 2000 epochs like that. They run it for the based on the number of epochs to ensure that the learning has been done. So at that time, whatever the weights you have, those 800 weights, where 600 weights between input 30 neuron input to 20 neuron output, and the 200 weights between 20 neuron hidden layer to the 10 neuron output layer, those weights will be stored as your main memory. Not main memory, but your final memory. And then what you do is you take the 30 images as the test images, whatever you have taken, and for every image, you use these 800 weights and make only one pass. and check whether the output, whatever you obtain, is equivalent to the desired or not. So if there is a match, if B equal to the output, then you make a hit 1. Or if there doesn't match, means D and the desired output is not matching with the predicted output, you say a miss. Then out of the 30 images, how many hits are there? Accordingly, you can calculate the accuracy of your multi-layer perceptron in identifying the digits 0 to 9. So like this, there are different algorithms as you proceed further. In this way, you have a different algorithms are there. So I'll stop here at this point for the classifiers, and then I move towards the clustering. So in the clustering, this is basically for unsupervised learning, where you have data with no labels. This is the main thing. Means the data will look like this. You have some data here. Since no labels, you have all the data which are similar to each other. So the typical example for clustering is if you go to the market and make a basket full of vegetables, purchase a basket full of vegetables where you have a bag. And when you come home, what you do is you segregate that into category 1, category 2, means all potatoes you group it, all tomatoes you group it, and all cauliflowers you group it, and then accordingly you try to clean them and put them into the refrigerator. So what it does is making the groupings. Clustering basically forms the groups. Means when you make one group here and one group here, the entities or the data present within this group are similar to each other, and they are dissimilar to the members of the other groups. So this is the underlying rule of the clustering. Any clustering mechanism, if you apply it, the data within a group are similar to each other, but dissimilar with the data of other groups. So this is the underlying rule for any clustering algorithm. So like this, you have a different clustering clustering algorithms available. Of them, some of the famous or the most popular we'll see. So you have different clustering algorithms, like let us say the simplest clustering algorithm is k-means clustering algorithm. Then you can have like DB scan is one, and the mean shift clustering algorithm is there. Then DB scan, which basically means a density based spatial clustering with noise. Then you have expectation maximization using Gaussian mixture models. So like this, you have many clustering algorithms are there. We'll see some of them at least within the time limit. So like this, you can have many. So this involves basically, as I told, clustering is grouping of the data points. So given some data points, we apply a clustering algorithm to classify or categorize each data point into a specific group. Let us see with the k-means. So this is the most popular or well-known clustering algorithm, which is basically not in any introductory classes. The advantage is it is very easy to understand and simple to code. Let us say you have some data like this available. So you have some data like this, and you have some data like this, and you have some data like this. Okay, you can put all these also layer classes. So you have some data which is been distributed like this. So on the plot, you can see that there are around 3 or different classes or groups you have. So the K here, it is similar to the KNN, but it is not the KNN. So here also K is, you need to give the input where K representing the number of classes you want to your clustering algorithm to divide the data into. So what we do is we take some the k input, and then we take each data point, we classify it with respect to the inputs whatever you have been given. Means if I say, let us say I take a k as 3, then what I do is I will randomly initialize 3 centroids are the central elements. Let us assume that those central elements are like this. I have randomly taken one center here and one center here and one center here. And what I do is I calculate the distances initially for every data point to these centers. Not only these, everything I'll do. And then what I do is based on the distances, I will try to get an understanding. So when you compute the distance between this point and the group center, then you classify it. So once you calculate, let us say you have n points are there totally, and you have 3 centroids are there. So from the 3 centroids, for every point, you are going to calculate 3 distances d1, d2, and d3. Then out of these 3, take the minimum d and then assign that center to the corresponding data point. So once you do that, what we do is you get the set of, you initially categorize every data point into the respective centers. And then what you do is remove the group center by taking the mean of all these vectors and initialize the center with the mean. So when I take, obviously since they are geographically located with these things, these points will be as having the distance minimum with this center, whereas a maximum with these centers. So these k points will be, let us say here you have k points, and here you have l points, and here you have n points, and n is the sum of all the k and l and m. So these k points, what we do is are been having the minimum distance with this center point, and what we do is we take the mean of these distances and then try to reinitialize the center with the mean of these points. So that can be any point like this. And then what we do is you get some new mean, new centers instead of these original centers. You calculate some new center, and then once again repeat the process as long as your centroids and your data will remain constant with every group. Here they will be constant within the second iteration or third iteration itself, you can see. But let us see points like this you have. means they are not separated well, but they are all like this. And here I want to make it as a k as 3. Then what I do is I have to have somewhere some sort of group such that I can make these as one group and these as another group or these as another group like this. I have to make it since I have my k is 3. Had the k is 2, I can make this as one group and this as one group. Or the same data, the main disadvantage of this algorithm is if I want to make, if I give k 10, then the algorithm will try to make it into 10 groups. If my algorithm k is 1, then the whole data belongs to one group. So in this way, this is called overfitting of the data, means trying to put it into one group. And let us say I have kn, means each data point is individually one cluster. This is called, this is underfitting and this is overfitting of the data. So this way, this is some, there are some disadvantages in this algorithm, but it is simple to understand like how you can assign. So the data which are similar here means when you say similarity between in this group and similarity in this group and similarity in this group means the distance, the similarity is in the form of the minimum distance from every point to the center. So this is a simple k-means algorithm which is very easy to understand. Then you can, the next algorithm is mean shift clustering algorithm. So this is like a sliding window based algorithm. So this what it will do is it tries to find the dense areas of the data points. So it is also a centroid based algorithm, means your goal is to locate the center points of each group. So even though it is a dense, it is also finds to locate the center point of each group by updating the candidates for the center points to the mean of those points within the sliding window. So these windows, whatever you define it, the sliding windows will be basically filtered in the post-processing stage to eliminate any duplicate also. So let us assume that you have the data which is being split, put like this. You have a lot of data which having some dense points at one stage and some points at this stage like this. So what we do is your mean shift sliding window, basically it's like you have a sliding window which is basically you can take a circular shape like this and keep moving this to the place where you have this dense area, where this in this dense area it will cover the maximum number of points, or keep let us have a bigger circle where it can include many items, and this point you can take it as the mean of all these points. It will be at obviously will be close to the center of this location. So this is how the mean shift means. As you move this sliding window, you are going to shift the center by taking the mean of those points which are covered within that window. So in order to do this, what we do is we consider we have a set of points in a two-dimensional space. Then what we do is we try to begin with a circular sliding window, having some center at C initially. The initial point is a randomly chosen center. This may be here, or you may get a randomly chosen center here also. And then you keep moving this randomly chosen center at different locations and then move towards the dense portion of the data. So this mean shift, it is like, if you know the artificial intelligence, it is like a hill climbing approach where the parameter for this total circular sliding window is the radius r, where we have a similar sort of a parameter in the hill climbing algorithm also. And the similarity between hill climbing and mean shift clustering is that both these approaches involve some kernel and keep moving the kernel iteratively to the higher density region on every step. Once you reach the higher density region, you can't move that window further, because as you move away, then your dense points will be reduced, and that will never allow that algorithm will never allow to move away. Means the point should be increased. Means the coverage should be more and more. At some point, you get the maximum coverage, that where you can see that the convergence has been arrived. So at every iteration, the sliding window, whatever you define it, will be shifting towards the regions of the high density by shifting the center of, so from here this is the center and here this is the center. So by shifting the center to towards the mean of the points within the window, you are going to further move towards the dense regions, and at this point you can't move further away. Means at this point you can say convergence has been reached. So this sort of a thing, you can use it. So once again, for this data, you can have a dense region here, and for this you have a dense region here, like that, and these things can be eliminated because they don't make any dense region. This is how the mean shift clustering will do. Then the other algorithm is density based spatial clustering with noise. So this we call DB scan. Okay, clustering of applications with noise. So S, C, A, and N, and density based DB. So this is a density based clustering algorithm. Similar to the mean shift, but what the change you can see from mean shift is that within a couple of, it has some even advantages also. So let us see how, let us assume that you have the data been sprinkled like this. Um, let us say you have some data like this. And then it has some points like this. And have a term like this. And you have some points here and some points here. Okay, so what your DB scan will do is it will start with some arbitrary position over that space. Okay, so it starts with some arbitrary point and then it keeps use a normal pen only. So it starts with some arbitrary position and it keeps moving towards the dense regions like this, and it proceeds and eventually at some point it will stop. Once you are done, all this data within this neighborhood is covered, and then it will start with another arbitrary point and another arbitrary point like this it will do. So this is how, means it starts with some arbitrary position, arbitrary data point that has not been visited, and it means when it is traversing, means all these points are totally visited, and so it is traversing, means it will keep track of every data point which are dense region like this, and tries to make that they have been visited, just like in your graph traversing algorithms like BFS or DFS. You label the vertices as visited or not visited by coloring them as white, gray, or black. Similar to that, it will do, and here also this is visiting of all these data points and all these data points within this. So what it does is it will start with some arbitrary point that has not been visited, and then try to mark it as visited, and then take the neighborhood of this point which is at the distance epsilon. So when it is taking another data point, so let us say it starts with some arbitrary point u, and the next arbitrary point is v. So the distance between v or u, distance between this u and v is epsilon, very small value. If they are at a small distance, then it will try to visit that, and then this v becomes next u, and next you can see the w point. Then you calculate the distance between v and w. If they are, and let us say that this is the point, after here you got this point, and this distance is not epsilon, it will ignore this and find some other point, so that it will try to find only the neighborhood points which are at a very small distance, not exceeding the epsilon, and cover all these points. And the mean of all these things, if you go through that curvature, this is how the grouping form. So if there are sufficient number of points within the neighborhood, then this clustering algorithm starts, and the current data point becomes the first point in the cluster, and it keeps moving this. Once it is done, it will check whether there are, once after this, it is not able to find any point which is at epsilon distance, then it will check whether all the data points have been converted their status into visited or not. If not, then it will again start with the vertex which is not visited so far, and then try to find the epsilon distance points from that particular vertex and covers this span. And once it is done, it will check whether still there are more vertices or not. If not, then it will go back and cover all these points. At this point, at some point of time, it will cover all the points, and at this point, when it checks for there are no points which are unvisited, then the algorithm eventually stops. So this sort of a thing, we call it as a DB scan method, which is a very efficient method in making clustering. Other than that, you have the other algorithm, which is expectation maximization, which is another algorithm which uses the Gaussian mixture models, and this itself is a little bit long concept, so I can't cover it right now here, but this is another efficient method to do the clustering, where it eventually finds Gaussian distribution of parameters is required to estimate the underlying distribution of the given data points. So overall, if you see the classification is assigning a class to every data point, whereas a clustering grouping the data points that are similar to each other. So at this point, I stop my presentation and I'll be happy if there are any queries for me.
Participants, if you have any queries, you may please ask. Or you can even post in the chat box. Are there any queries for sir? You can either unmute or you can post it in the chat. Okay. So I think.
So we can say that underlying interpretation, whether all of you have understood or none of you have understood, either it is underfitting or overfitting of the data.
I think we can have few feedbacks. Maybe participants can just share how was the session and what was their takeaway also. So you're most welcome to unmute and answer, or you can post it in the chat box.
I think there are no queries.
Yeah.
Yeah.
So
And,
thank you so much, Dr. Chandra. It was really a very good session.
Thank you, ma'am, for giving an opportunity for me to interact with you.
I wanted to thank you, sir, for accepting the invitation and taking this wonderful session. Thank you once again, sir.
Yes, thank you, ma'am. I think I can leave the meeting, right?
Yes, sir.
Yeah, thank you.